Now I'm going to do two interesting things. One is I already know for a particular input the response of this particular system. I would like to verify that using the convolution theorem. And if I say that the natural frequency of this system is omega, the time response is plotted over here, which is given by, in the time domain it is just f naught. This a belongs to this because we remember we multiplied and divided by a. Now, one of the philosophies at Innovent, what we have been pursuing is everything that you do must be correlated with a practical application, because mathematics is for practical applications and they are not meant for mathematics, right? So now I would like to exploit the convolution theorem, which in fact provides you the inverse Laplace transform of two functions. When you convolve two functions, you will get the inverse Laplace transform of that particular set of functions. I want to correlate that with a physical system. Now I'm going to do two interesting things. One is I already know for a particular input the response of this particular system. I would like to verify that using the convolution theorem, whether the physical result that I get is actually correlated with the mathematical fact of the convolution theorem. Convolution theorem is supposed to give you the time domain response for two functions whose Laplace transform is known, right? You first take inverse Laplace transform, then implement that in the integral, and you get the time domain response. But if I know a time domain response for a particular system, can the convolution theorem prove that it is exactly the same time domain response? It is like a verification of two facts. Okay. Now, this spring mass system, I don't want to get into the details of it. And if I say that the natural frequency of this system is omega, the time response is plotted over here, which is given by 1 minus cos omega t multiplied by f naught by k, where this system is subjected to a constant step force f naught. This is also called the step function whose amplitude is f naught. A constant force this system is subjected to, that is f naught, and the response of the system is given by this. There are several methods of arriving at it. Let me not confuse you with a lot of physics and solution of differential equations. Since in the first year mathematics of engineering you have dealt with differential equations, even if you form the differential equation and solve this particular system, you will get this response indeed. Very, very simple to get this. And you can see that this is f naught by k, which is also called the static amplitude or displacement, and this is 2f naught by a and k, which is also called the dynamic amplitude, right? So these are two jargons, but forget about all that. What we have essentially here is this is a system, you're subjecting the system to a step force, and this is the time domain response, right? So now let us try and derive it using the convolution theorem. Now, how would you actually conceive the convolution theorem? For that, you need two Laplace transforms. Now here, in this context, because we are making it everything correlated to a practical situation, this represents the transfer function and this represents the input. If you have any confusion or doubt, please go back to our lectures, introductory lectures, where we have detailed as to what exactly is a transfer function and what exactly is an input. Now we can get expressions for this. It's quite easy because we are talking about a spring mass system. In the introductory lecture, we did explain how to get transfer function for a spring mass damper system. If I drop the letter c, that is c is equal to 0, then the transfer function that I'm going to get is m s square plus k, right? And if I assume m is equal to 1, the transfer function that I am going to get is s square plus k. I would do one more step here for mathematical convenience, because I know this is the Laplace transform that represents the transfer function of the system. But in order to implement in the convolution theorem, I need inverse Laplace transform of this. And in order to get the inverse Laplace transform of this must fit into the definition of any standard function. And you can readily see that it fits into the definition of sine AT, provided this is assumed to be square of some constant. Instead of saying k, can I say a square? It makes no harm, because I'm just replacing one number by another. It is like saying 2 is replaced by root 2 whole square. That's all I'm doing, right? So what happens, this is equivalent to saying 1 by s square plus a square. And what I can further do is multiply and divide by a. Why I am doing that? Because this facilitates me taking the inverse Laplace transform of this, because this definition is that of the sine. By now you are absolutely familiar with this. That is, this is the inverse Laplace transform of sine AT, and that can be done by multiplying and dividing by a. So one function is got. That is, we are done with g of s. So let me recollect what we did. We actually started with this system, and this is the typical time response of the system, and this is subjected to a step input, that is f0, constant amplitude. And I want to prove that whether I will be able to get the same time response if I implement the convolution theorem by knowing the Laplace transform of the input and the Laplace transform of the transfer function. Transfer function, of course, is Laplace transform. So transfer function and input function, if you know, would you be able to get this response without solving the difference? Here, what we would have done, we would have solved the differential equation of this system, and we would have got both particular integral and complementary solution, which you have done in your first year, and got to the solution. But we don't have to do all that if you just know the Laplace transform. So this is easy to get. This is the standard transfer function of a physical system, spring mass system. Now I need to know the transfer function for the input. So input is a constant f0, okay? And if you take Laplace transform for any constant, it is commonsensical that you get f0 by s. We have proved this umpteen number of times, because it is like integrating e power minus st into 1 into dt from 0 to infinity, which obviously gives you 1 by s. So now I don't have to do any solution of differential equation or find particular integral, complementary solution, nothing. I have a ready tool called convolution theorem. That is the advantage. Mathematics must always be used to apply in a physical situation, okay? To get insight into a physical situation rather. So now I have got the transfer function, now I have got the input function. All that I got to do is implement all this understanding in the definition of convolution theorem. It's going to be interesting, because this is the first problem where you would be using the definition of convolution theorem. So not only that, you get an insight into what exactly is going on, how the convolution theorem is applied in the context of a spring mass system, but also you will be able to appreciate the procedure of implementing the convolution theorem. So let's move on. Now, what is the first step? First step is to write the definition of convolution theorem, which gives you the inverse Laplace transform of g of s into f of s. Till far, in most of the textbooks and university classrooms, you would have just deemed upon these two as two functions. But here, we are giving you a physical connotation of what is going on, and the physical connotation of g of s is the transfer function, and the physical connotation of f of s is the input. Transfer function multiplied by input will give you the output, and output, if you take inverse Laplace transform, that gives you the time domain response. Very simple. So let me write the connotation of the convolution theorem, rather the definition of convolution theorem here. We have given the connotation of these two functions, and the definition of the convolution theorem is f of, or if I say g is my first function, g of t minus u, okay, multiplied by f of u integrated with respect to u, and the limits are u is equal to 0 to u is equal to t. This means what? since I'm taking a variable u for integration, of course this turns out to be a function of t. So since I'm integrating with respect to u and putting the limits of t, this must be a time domain function. This also must be a time domain function. As a consequence, what should I do? I should get the time domain definition of g of s, time domain definition of f of s. F of s I don't have to struggle, because the system is subjected to a constant force f naught. It is not a function of time, it's a step input. So therefore I can readily write the first expression over here. It is f naught and du. Now I need the definition for g of s. So that is why we very tactically said that we would put k is equal to a square and multiply and divide by a, because I can fit the definition of sine at to the g of s, right? If I take the inverse Laplace transform, it is nothing but sine at by a, because you carefully observe here that this definition fits into sine at. So my second function is also quite easy to choose. This is nothing but sine at by a. And if I have to write in this particular form, all that I got to do here is just to replace t by t minus u. Remember, you are replacing t by t minus u, and then of course a continues to piggyback. So this a I have written here, and this function I am going to write here. So what is that going to be? Sine of a inside the bracket, it is t minus u. Remember, the second function you replace t by u, and the first function you are going to replace t by t minus u. That's all you do once you take the inverse Laplace transform. Let me explain once again. This is the definition of convolution theorem. First you identify g of s, f of s, then take inverse Laplace transform for g of s and f of s both, and once you do that, you just implement over here. All that I got to do is basic integration. Not even the integration is complex here. It's very plus 2 kind of integration. This is f naught by a. Let me not write in advance. That's what I'm going to get. So f naught by a, and what you have here is integral 0 to t sine. In fact, a here you're replacing by t minus u, and you are integrating with respect to u. So what it is going to be? It's going to be very simple. Remember, whenever you integrate sine, you get minus cos, okay? Of course, at minus au. Just to avoid confusion in brackets, I just multiplied inside. And this is going to be divided by the integration is with respect to u. Remember, t is a constant here. Integration with respect to u. Of course, the limits are 0 to t, but when you are integrating with respect to u, so t has to be treated as a constant, and therefore you are going to divide this expression by the coefficient of u, which is minus a, right? So that is to be understood carefully. And what are the limits? 0 to t. And minus would get cancelled. A I can take out, f naught by a square, and I am already there for the final result, because this would get cancelled. What you are left with is just cos. When you put u is equal to t, this becomes cos 0, which is 1, minus. If you put u is equal to 0, you will get cos 80, and this is what exactly we were supposed to get. What we said? We said k is equal to a square. So I can as well replace a square by k, because that was the assumption that we made. And now I have got cos at. A is nothing but omega t. I will argue that. Why? Because the natural frequency of a system is given by root of k by m. In algebraic terms, it is the stiffness and the inertia that determine the natural frequency of a system. Root of stiffness and inertia. And if I assume stiffness to be a square, which I have made here, which sounded highly justified because we wanted to fit in the definition of Laplace transform of sine, and m, of course, we assumed in the beginning of the discussion to be 1, and obviously this turns out to be a, because root of a square by 1, which is a, and therefore this a is nothing but omega. And look at here, your physics is proved by your mathematics. So we started with this standard time response of the system, and when we verified, can I achieve the same response provided you have the connotation, or rather the definition of transfer function and the input, right? Then this becomes a very, very simple thing to follow. So suppose, just look at the amount of effort that the Laplace transform is saving for you. Suppose if you wanted to model this system, solve for complementary and particular integral, applying all the boundary conditions, it would have taken significant amount of time. But here you just had to know what is the transfer function of the system, what is the input, and this integral was very, very easy for you. And when we did this, you could see that you got exactly what you were expecting, right? So let me walk you through what transpired. So this is how powerful is the theory of Laplace transform. What we wanted to understand in this particular context is we started with a spring mass system, and we know this is the response of the system, which is plotted here, which turns out to be 1 minus cos omega t, and it is even to guess this solution is a good amount of common sense if you are familiar with the vibrations, a rather simple harmonic motion, I would say. But however, it can be solved using basic differential equations. That is the second order differential equation that you form for this system. If you are able to find the particular integral and the complementary solution, and using boundary conditions, you can get this solution, number one. Number two, this system also can be characterized in terms of the Laplace transform, the transfer function and the input, because we said this system is subjected to constant force F0, and therefore we could get the Laplace transform of the input to be F0 by S, because you know for a constant the Laplace transform is 1 by S. So for 1, if it is for constant, then constant by S is the Laplace transform. And for the spring mass system, this is the Laplace transform, because you have already seen this when we did the introductory lecture, and we also explained you what is a transfer function. It is got by transforming the differential equation by assuming 0 initial conditions, and then this, when multiplies the input, that is F0 by S, will give you the system response in terms of frequency domain. And of course, when you take the inverse Laplace transform, you will get the time domain response. But here, what is the technique that we are applying for inverse Laplace transform? The convolution theorem. We have seen several techniques, but convolution theorem is one of them. So now that we know the Laplace transform of the transfer function, that of the input, we are trying to use the convolution theorem to get to the time response. So how do you actually apply the convolution theorem? This is the definition. U is a variable here. Inside the integral, t must be treated as constant. We need the time function of the equivalent time function, that is of the transfer function, the equivalent time function of the input, and this is how we do. We know that the transfer function has a sine at by a, which we have explained, and the input function is simply F0. The only thing that you got to do is the first function is going to have, instead of t, t minus u. The second function would have t replaced by u, but since it is a constant function, it doesn't matter. The second function F0 by a, and the first function is nothing but sine a into t minus u by a. Of course, this a belongs to this, remember, because the second function is a constant function when you take into time domain, but in the frequency domain it is F0 by S. In the time domain it is just F0. This a belongs to this, because we remember we multiplied and divided by a. And once we integrate this, which is quite simple, because sine, if you integrate, you'll get minus cos, divide that by the coefficient of u, because you are integrating with respect to u. And when you substitute the limits, when you put u is equal to t, this becomes 1 because cos 0, and when you put 0, it becomes cos 80, and finally you get to this expression, and we here extremely clearly and categorically recognize that k is a square. So here I can replace a square by k, and also I proved that this is the definition of natural frequency, which depends on inertia and stiffness. right? Inertia and stiffness, which determines the natural frequency, and therefore K if I replace by A square, M if I put as 1, then I'll get A as the natural frequency, and this definition or this answer what we got using convolution theorem exactly fits what we were anticipating, right? So therefore the convolution theorem has a connotation in the realm of engineering applications, and that is what we were trying to unravel. So the most powerful message that you take home is, instead of spending so much of time finding the solution of the differential equation of a system and then understanding the time domain response, in a very, very quick and efficient way, you can apply Laplace transform to get to the time response. All that we did was to develop the transfer function and know the input, and then use the convolution theorem to get to the time response. So let's move on and look at some typical university problems using convolution theorem. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.